Multivariable Calculus, Section 13.6. Triple integrals. You are going to love them. Let's review double integrals. If we have a double integral, then the function has to be a function of two variables with respect to the area of a region R, where R is a region, two-dimensional region on the xy plane. If f of xy is greater than or equal to 0, then the double integral returns the volume between the surface described by f of xy and the xy plane. If f of xy equals 1, then the double integral returns the area of the region R because you're making the height 1 unit. And if we split the double integral with separate limits of integration for x and y, then we call that an iterated double integral. Introduction to triple integrals. If we have a triple integral, then the function has to be a function of three variables. And T is a solid region in 3 space. Previously we integrated over R, which was a region in 2 space on the xy plane. So now we're integrating over a solid region. And if f of x, y, z equals 1, then the triple integral will return the volume of the solid described by T. And if we split the triple integral into 3 separate integrals each with their own limits of integration, then again this is called an iterated integral, in this case an iterated triple integral. If f of x, y, z doesn't equal 1, then the triple integral returns the hypervolume of a 4-dimensional object described by the function of 3 variables. So we're going to jump into the problems. Evaluate this triple integral if the function is xy sine z and t is the cube defined by x, y, and z greater than or equal to 0, which means you're in the first octant, and also less than or equal to pi. So you have a cube that's pi by pi by pi. So that means x, y, and z are all going to vary from 0 to pi. And then we have to decide what order should we integrate in. We can do it in any order, but we want to use the easiest possible order. So I chose to integrate with respect to z first. That way I won't have a 1/2 y squared or a 1/2 x squared right off the bat. And then it doesn't really matter if we do dx or dy next. So integrating with respect to z, we get negative xy cosine z, and we have to evaluate then z from 0 to pi, and that gives us the integral, the double integral of 2xy dx dy. And so that's convenient because now we can integrate with respect to x and get x squared y and substitute 0 to pi for the x value, and that gives us the integral of pi squared y dy, which integrates easily. And then we have to evaluate that from 0 to pi, and we get our answer of 1/2 pi to the 4th. Now notice that our function can be separated into the product of 3 functions, one in terms of x, one in terms of y, and one in terms of z. And we talked about that in an earlier lesson. And so we could have integrated differently. We could have made this triple integral into a product of 3 single variable integrals and done it that way. So we would get we would evaluate each one separately and still get the same answer. This won't happen very often, but if it does, this is a nice little shortcut. Number 10. Evaluate this triple integral given that f of x, y, and z equals z, and t is the region between the surfaces described by z equal y squared and z equal 8 minus y squared, whereas x goes from -1 to 1. So right away I know that I'm going to integrate with respect to x last because it's going from -1 to 1. And then we've got z in terms of y, so we're going to have to integrate in terms of z first for 2 reasons, because we've got nice y limits set up, and also our function just equals z, so that'll be easy to integrate. Okay, so here is the region on the zy plane, because those are the two functions I'm given. And so we can see that z is going to go from the lower parabola up to the upper parabola. And then y can then go from, it looks like -2 to 2, although we might ought to check that out. And then the solid is given by taking that region and scooting it backwards 1 unit and forwards 1 unit. So it looks something like that. All right, so again, here's an arrow showing the way z has to travel from the lower parabola up to the top parabola. And just to check this out, we're going to set those two y expressions equal and solve, and sure enough, we are going to let y go from -2 to 2. So here comes our triple integral. And then we're going to integrate with respect to z. So we're going to get a half z squared evaluated from 8 minus y squared to y squared. And then we can bring the 1/2 outside and simplify our integrand. And now we can integrate with respect to y. And I brought the 1/2 in. So let me just check that real quick. The derivative would be 32 minus 8y squared. Yep, so that's correct. And we're going to evaluate that from -2 to 2. So now we have 256 thirds in our integrand, which integrates easily. We're going to evaluate that from -1 to 1. And we get 512 thirds as our final answer. Number 12. Sketch the solid bounded by z equals y, y equals x squared, y equals 4, z equals 0, and then compute its volume using a triple integral. So the first thing I did was draw the parabola y equals x squared, and notice I've changed the way I drew the axes to make that easier, and then cut that parabola off at y equals 4, the horizontal line y equals 4. And then that parabolic region moves out towards you along the z-axis. And I noticed that if I combine the z equal y, y equal 4, and z equals 0, that means z would travel from 0 to 4. So now I have this part of the solid. So then the next thing to do was to draw the plane z equals y. And that took quite a little bit of thinking. Notice that you're looking at the zy plane from behind. And so to make sure I got the line going the right way, I plotted a couple of points. If z is equal to y, then for example 0, 0, 0 is on the plane, and 0, 4, 4 is on the plane. And so there's your line z equal y on the zy plane. On the zy plane, and then you move that line segment along the x-axis to see where the plane is. So the solid that we're computing the volume of is above the plane z equal y, below the plane y equal 4, and then trapped on the xy plane by the parabolic region. So it's the top half of my drawing. And so now we're going to set up our triple integral. Notice that there are no functions for x. X doesn't equal anything in terms of the other variables, so we're going to integrate with respect to x last. And from the graph, pretty obviously, x is going to go from -2 to 2. So then the next integral has to hand off x expressions for an x function, and that means we're going to do y next. And y goes from the bottom of the parabola, x squared, up to the cutoff, the horizontal line, y equals 4. And so then that leaves us with dz as what we're going to integrate with respect to first, and z travels out from the xy plane where z equals 0 to the plane z equals y. And so z is going from 0 to y. Also, the function that we're integrating is 1 because we're computing volume, not hypervolume involving a function of 3 variables. So the integrand is just 1. So now we integrate with respect to z, and we get the antiderivative of 1 is just z, and we're going to substitute y minus 0 for that. And so we just get y, and then we integrate that with respect to y and get a half y squared, but we have to substitute for the y squared, we have to substitute 4 and x squared. So we get a half 16 minus x to the 4th, And then that one integrates fairly easily. 16x, a half the quantity 16x minus 1/5 x to the fifth from negative 2 to 2. And using a calculator, we can get the answer of 128 over 5 rather quickly. So now I'd like to take a look at a problem from a different textbook that presents some difficulties I couldn't find in the examples in your textbook. Compute the volume of the solid region inside the cone z equal x squared plus y squared and between the planes z equal 1 and z equal 2. So the red region is the volume we're trying to compute. And because we have z going from 1 to 2, we might think, well, let's just put that on the outside integral and let's look at x and y. So you'll notice that x always, if we do that first, it travels always from one side of the cone to the other side of the cone. And that depends on how y and z are changing. And then if you look at y, then once we eliminate x, we'll do that first. Once we eliminate x, then we flatten this whole thing down to the yz plane, sort of. So that would mean that y is always going to travel between those two lines. And then finally, then we can let z go from 1 to 2. So here's what our triple integral looks like. We have a 1 in the integrand because we're doing volume. X is going to travel from one side of the cone to the other, and I got that by taking z equal the square root of x squared plus y squared and solving for x. And then y is going to travel between those two lines, so basically negative z and positive z since they're at 45-degree angles. And then finally, we integrate with respect to z from 1 to 2. So let's see how that works out. We'll integrate with respect to x and substitute our limits of integration. We'll get an integrand of 2 times the square root of z squared minus y squared. That's not a very easy integral to do. You could, however, use trig substitution and let y equal z sine u. Well, I did that on some scratch paper and did some simplification and came up with this integral, which is not too thrilling. Now, it actually does work out. I had to do quite a lot of scratch on my scratch paper, and I did use an identity and integrate and so on and so forth. But it took a little while. So that's probably not the best way to do this problem. Well, let's not make babies cry. Let's look at it a slightly different way. So we would like to probably integrate with respect to z first, which is what we usually do. And z is a function in terms of x and y, and so we could hand off our answer to x and y to do the middle and outer integral. So that would be nice. But the problem is this red volume is not vertically simple with respect to z, because in the middle, z is moving from the bottom plane to the top plane, but on the edges, z is moving from the cone's edge to the upper circle or plane z equal 2. And so that's a problem. However, we could do the entire cone if we let z always move from the cone up to 2, and we let x move from one side of the circle to the other. Then we can let y finally go from negative 2 to 2 for our outer integral. But I'm also noticing here now at this point that these limits of integration are reminding me of polar formulas. If we try to integrate with respect to z and then substitute the square root of x squared plus y squared, that's going to be hard to integrate. However, if we change to polar, we get one integral for the entire cone. This would be the entire cone, changing dx dy to r dr d theta, and then z is always going to go from the radius, because z is the square root of x squared plus y squared, which is the square root of r squared. So z is going to go from r to 2. The r, the radius, goes from 0 to 2, and then we're going all the way around the circle, so theta goes from 0 to 2 pi. So this integral will give us the entire cone. And from that we can subtract the blue part of the cone, and that will give us the red. So for the blue part of the cone, the only changes are that z is now going from r to 1, and the radius is only going from 0 to 1. So let's evaluate those integrals. Integrating with respect to z, we get rz, and then we substitute our limits. And then integrating with respect to r, we get this. And I'm running out of room, so let's clear the board a little bit. Move that up to the top. Substitute 0 to 2 and 0 to 1. And then finally integrating with respect to theta, we get 7 pi over 3. Phew. Now, in actuality, we could have done this problem a lot more easily with geometry because the volume of a cone is given by 1/3 pi r squared h. And so if we take the whole cone and subtract the little blue part of the cone, we do in fact get the same answer in a few seconds. But it's nice to know that the calculus works, eh? Number 20. Sketch the solid bounded by y = 4 minus x squared minus z squared, x plus z equals 2, and x, y, and z all equal to 0, and then compute its volume using a triple integral. So this information right here, if x is 0, that's the yz plane. If y is 0, that's the xz plane. And if z is 0, then that is the xy plane. So I'm going to start my drawing in the first octant and see if that's going to be sufficient. And we'll start by sketching the traces of this solid on the 3 planes. So for example, if I set y equal to 0 and then move x squared and z squared to the other side, I get a circle. And so in the first octant, I get 1/4 of the circle there with radius 2. And if I set z equal to 0, then I get y = 4 minus x squared, which is part of a parabola on the xy plane. And if I set x equal to 0, I get y equals 4 minus z squared, which is the same parabola, only drawn on the zy plane. And so we can see what the solid would look like in the first octant using that first equation. So now let's move on and see what the plane x plus z equals 2 looks like. Notice that that's the same as z equal 2 minus x, so in the xz plane, I'm going to draw that line and then extend it out along the y-axis. And so what's happening is that plane is cutting off the top of that little bubble-shaped solid that we had before. And so the solid then comes up from the xy plane and hits part of the bubble and part of the plane. So now we need to set up our triple integral, and again we chose to rewrite x plus z equals 2 as a function of z. We could have done it the other way around, but we're going to do it this way. And so that means I'm going to integrate with respect to x last because I don't have any functions x equal anything. And x is going to go from 0 to 2. Just looking at the graph we can tell that. So then the next one I'm going to integrate using z because z has to hand off an x function, and y is not expressed as a function in x alone, but z is. So z is going to go from 0, that means the xy plane, up to the plane described by x plus z equal 2. And so z is going to go from 0 to 2 minus x. And then finally, we'll integrate with respect to y first, and y goes from 0, which would be the xz plane, out to the bubble, which is described by y = 4 minus x squared minus z squared. And then again, the integrand is 1 because we're doing volume here. So we integrate with respect to y, and the antiderivative of 1 then is y, and we substitute the two limits, and so we just get 4 minus x squared minus z squared dz dx. And then we integrate that with respect to z and substitute 0 and 2 minus x for the z values. Of course, when you put 0 in, you're going to get 0. So basically, we're just substituting 2 minus x for each of those z values. And that's going to be integrated from 0 to 2. Now you can multiply that and do the algebra and do it by hand, but I chose to use a calculator to finish it up and got 16/3. Number 24, find the centroid of the solid bounded by z equals 1 minus x squared, z equals 0, y equals negative 1, and y equals 1 of uniform density 1. All right, so z equals 0, what does that mean? That's just the xy plane, so that's nice. The whole thing is above the xy plane. And so I drew the parabola z equals 1 minus x squared on the xz plane, and then moved it up and down from negative 1 to 1 on the y axis. And so there I have another parabolic cylinder. Okay, so then we need to set up our integral. And for mass, we integrate the density with respect to the volume this time. Before, in the previous lesson, we did it with respect to the area, but now we have a triple integral, so it's with respect to volume. And notice that it is simple in the direction of the z-axis, so we're going to integrate with respect to z first. So the integrand is 1, and z is going to go from 0 to 1 minus x squared, and then we can do dx and dy in any order we like. So I just arbitrarily chose dx, dy, and both of those are moving from negative 1 to 1. And so the antiderivative of 1 is just z, and we substitute 1 minus x squared for z, and 0 is just going to be 0. Then we integrate that with respect to x, and we get x minus 1/3 x cubed evaluated from negative 1 to 1, which comes out to 4/3. Integrate with respect to y, we get 4/3 y evaluated from 1 to negative 1, and our final answer then is 8/3 for the mass. Okay, so that's the mass. Now, we can look at the graph, and pretty obviously the x bar and y bar are going to be 0. Because those are the center points. And so it's only z bar that we have to compute. Z bar then is going to be the reciprocal of mass. Same integral, only we have to integrate the density times z. And so the antiderivative of z is 1/2 z squared. We substitute the 1 minus x squared and the 0 just gives us 0. And so then we integrate that middle integrand there with respect to x, but I didn't feel like multiplying it out. I got a little lazy, so I just evaluated that circled part of the problem with a calculator because it's going to be numeric, and that came out to 8/15. So now we have 3/8 times 8/15, which is 1/5 dy, and the antiderivative of that would be 1/5 y, and we evaluate that from negative 1 to 1 and get a final answer of 2/5. So our centroid then is the point 0, 0, 2/5. So now let's have a summary here of the general idea of what we're doing. When we have a triple integral, we are integrating over a three-dimensional region. And we might be integrating 1 and thereby getting the volume of this three-dimensional region. Or we might be integrating something more complicated and figuring out moments of inertia or density or centroids or a four-dimensional hypervolume or something like that. But regardless, when we have a triple integral, we are integrating with respect to z, with respect to x, and with respect to y in some sort of order. And we have various ways of deciding which variable we're going to integrate with respect to first. So let's say we've decided we want to integrate with respect to y first, and that dy then is going to go in that innermost position. Well, what we have to have then for our limits of integration, the limits of integration have to somehow be in terms of x and or z. And once we do that integration, we've eliminated y. And so if you think of it, you're projecting the whole solid onto the xz plane because we're eliminating the y-axis. And so now we've got a two-dimensional region over which we are integrating. And we have various ways of deciding then what comes next. In this particular case, we're going to integrate with respect to z next because this particular area is vertically simple but not horizontally simple. So our innermost not our innermost, our second integral then is going to have a dz. dz is going to be in the middle position. And our limits of integration in that middle integral have to only involve the x variable. So once we do that integration then, we've eliminated z, and we're down to a single integral. And so basically you're projecting this two-dimensional region onto a one-dimensional region, onto the x-axis. And so we've eliminated z completely, and now we're integrating along the x-axis, and so the limits of integration have to be numeric. The number on the left and the number on the right is what we would use. All right, now maybe we're going to do this problem, we're going to set up the integral in a different order. So let's say we want to integrate with respect to z first. Then what we're going to have to do is eliminate z, and so our limits of integration there in the middle inner integral are going to have to involve only x and y. And then what we're going to do when we integrate with respect to z is basically we're going to take this solid and project it down onto the xy plane, and thereby eliminating z after we integrate that inner integral. So then we have to integrate either with respect to y or with x first. In this case, probably doesn't matter. We're going to have to create, it looks circular, so we're going to have to create two functions, a positive square root and a negative square root. So let's just say we decide to integrate with respect to y next. Then our limits of integration then on that next integral, which is in between the inner and the outer, those limits of integration will have to only involve x. And once we integrate with respect to y and substitute expressions in x, we've eliminated the y variable and the y axis, and we've projected that 2D object onto the x-axis. And so that final outer integral with the dx has to have numeric limits of integration. Whatever the number on the left is goes on the bottom, and whatever the number on the right is goes on the top. So that's the general idea behind what we've been doing. News Bulletin. Fermat's last tweet has been revealed. I have discovered a truly marvelous demonstration of this proposition that the 140 characters of this tweet are too narrow to contain. And now it's your turn to do the homework for section 13.6. Enjoy.